Okay, Bismillah Rahman Rahim. So, the today's topic is design of bolted joints, and the idea of recording this lecture is because there is a left time available before mid exams. So, I just want to cover this topic through video lecture. So, bolted joints are generally, if you have seen bolts, these bolts generally have threads, and these threads are generally machined on a cylinder. So if you have a very simple cylinder, yeah, and I think you have done in your first year using lathe machine, in which let's say you have a simple cylinder, the cylinder like this, and just you put it on a mount it on a lathe machine and just provide threads over it. The idea of providing these threads is you required fastening, you required to connect two parts, and the easiest way of doing it is using the bolted joints. The bolted joints generally have, let's say, mostly they're used in covers or in plates or in between two assemblies, and the idea is to connect these two parts. The idea is to connect these two parts temporarily, which means you can open it, and the bolts are generally used on the places where maintenance is continuously required, like in machines, in engines, and all these things, in which you know that the maintenance is a routine part of that particular machines. So the bolted joints has a unique importance in engineering, especially mechanical engineering. And today's topic will try to design those bolts, and how we find the stresses and loads, and based on those how we can design the bolts. So before going on to the design problem, we will see some theory behind these bolted joints. The bolts also has three main characteristics, or you can say three main shapes. They are all threaded joints, but if you have a head, generally it's a hexagonal head. It's not necessarily it must be hexagonal. It can be a square head, but generally in market the available bolts are with the hexagonal head. And hexagonal head, what I means from hexagonal head is the shape of the head is looks like this. So it's six corners, clear, and your wrench set also have these heads which you can tight or loose the bolts. The bolt also contains a nut, so we have this whole assembly is a bolt, and this assembly we call as nut. This nut is used along with the bolt, so you can fasten two plates or two different parts, and we can also we can open it when we want. In case of screw joints, we do not have a dedicated nut, but what we actually do is we provide internal threading to any part. Let's say if you have a thick plate and you cannot pass through the bolt, and that is very common in assembly of car engines. There is a bolt, but you do not have a nut over it, so you provide internal threading using tap set or tapping, and then you tie the bolt within that internal threading. This is generally called a screw. And if you don't have any head, which means this is nut, and you have a simple threaded cylinder like this, you just put it tighted cylinder in this internal threading, and then put a nut over it. So it is called stud. Stud is generally used where you required your length of your desire. Like if you go to a market and want to buy a bolt, so bolts are generally available in standard sizes like 6 inches, 1 feet. If you want a bolt size of let's say 10 mm, and you want bolt length, the shank length, generally shank is the body of this bolt. So you ask that I require shank length of let's say 7 feet. So these bolts are not available because standard lengths with the let's say 10 mm bolts are generally not more than 3-4 inches. Now instead of using standard bolts, you can use studs. Now studs are the long threaded cylinders. They do not have any head, but you would go to any hardware shop and ask him, I want stud, I want threaded cylinder, मुझे चूड़ी वाली वो चाहिए, या मुझे बगैर हेड के मुझे बोल्ट चाहिए. Generally they are called studs. So they are available in lengths of 10 feet or large, and you buy nut separately, and wherever you want that nut to be tied, you can tight it at your own desire. So studs are generally used where you require large lengths and standards are not available. But disadvantage of using studs is they do not have as strong head as compared to a bolt, because bolt the head of the bolt is machined or manufactured along with this shank, whereas you provide separate threads. So this whole thread, the connection between the shank and the thread, so you can see if you have a bolt over here and you have a shank, so this is the area which is actually in contact with the head, so it can bear large stresses. Whereas if you look at this nut, it's only can thread this, it just, I just want to draw like this. If you have internal threading like this, and if you want to tight a bolt, so you can say that we have okay, just 1 minute, I want to change the color of that. Okay, so if I want to tight a bolt, so I have a bolt like this, so I have a body, so it's tight like this, yeah. So it's actually matches with the threading of this. So see, the only contact area in between this, the internal thread and external thread. So in case of studs, you have only the stress beared by only the threads, not the head. So that's why studs are not as good in bearing those stresses as compared to a bolt. But yes, as I mentioned earlier, they are customized. You can use in very large length, like in feet, or also where bolts are generally available in standard sizes. Okay, now this is how you tight a torque, and to tight every bolt and nut has a certain torque. It's called tightening torque, and tightening torque is generally a very important factor in actually saving a bolt from failure. Is that every nut bolt, based on the material, based on the dimensions, the size of the threads, the diameter of the bolts, and all these things, the bolts are generally tighted using a torque wrench. So we have a torque wrench, we call as torque wrench. It is generally expensive. Normal wrench are available like in cost of 1 or 2,000 rupees, where a torque wrench nowadays costs around 100,000, which is around 1 lakh or so. They're expensive. But the idea of using torque wrenches, and they're used in most sophisticated environments like the car assembly plants, or where the machine has been manufactured, the large machine has been manufactured. The torque wrenches actually, you can set a torque on it as much as you want, and when this torque is achieved, this torque wrench actually indicates you by clicking sound, like tick 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 tick. So it's do not actually provide a sound if the torque is not achieved. So if you, let's say, I'll just give an example. So for example, the car engine bolts, car engine is used to connect the head and the cylinder of the engine. The bolts generally required a torque between 80 to 100 Newton meter. So these are by design, and this is written in their maintenance catalogs of like Toyota, Honda, or Suzuki. And if you set your torque wrench to, let's say, 100 Newton meter and start tightening that, because it's the torque wrench, similarly it's a wrench, but on the other side where you actually hold the wrench, like this person has held here, the idea is you can set the value, and then when 100 Newton meter is achieved, the clicking sound is there. So you know that already, that the torque, the bolt has been tightened by 100 Newton meter torque. This is not a common practice in you can say in generally workshops, because this torque wrench is expensive. That's why generally people use normal wrenches, and provided the hand force, which even they don't know what force is required, and they just apply as much force as they can to tight a bolt. So yes, it actually affects the life of the bolt, especially if you're talking about the bolts in industry. Okay, the materials are generally for room temperature, like 30, 40, 50 degrees centigrade. You can use low carbon steel or medium carbon steels. Mild steel is a very common material used to manufacture bolts. And if you go to any hardware store and ask him to give you a bolt of 12 or 10 or 14 or 16, they give you a bolt. This is general purpose bolts, and they're generally made of mild steel. Mild steel is a cheap material. It's a mild steel, it's a medium carbon steel. So they have been used, and the boards generally reasonable prices. But if you use the boards that are actually at the high temperature, they are generally used in engine assembly, like in crank assemblies, or where there's a very high temperature. So we use titanium as alloy, or chromium, or manganese. So these are expensive. Yes, if you want to buy a bolt that are used in the crank assembly, the bolt set cost about 12 or 1300 rupees. Just give an example. At the same size of bolt, there is no difference of design, but only the difference of material. If you want to say the same dimensional bolts, a general purpose dimensional bolt with the same thread size and all these things, it cost about 1 by 10 times. Means if your car bolts cost around 1200, they cost around 100 or 120 rupees. This is a difference between at room temperature, like if you use in brackets or in assemblies, larger assemblies, like in industry, where the temperature is not high, you can general purpose bolts, mild steel, low carbon steel, they work fine for us. But for high temperature application, like temperature like 400, 500 degrees centigrade and even higher, you require the alloy boards like titanium based alloys, or chromium based alloys, or manganese or cobalt, or like these things. So yes, they become expensive. Okay, so how many heads a screw has? Now when you talk about screw and head, most people are confused by the bolt and the screw. As I mentioned the first slide, bolt is generally contains a nut, whereas screw are generally used where there is no nut. Actually, you do not put nut, the threading is internal. Either you provide the pre-threading, or in case of wooden assembly, the thread will be made by the screw itself. So there are different type of heads, as you can see. It could be hexagonal, philister, round, flat, hexagonal, flatted, and even it's called the cross head. There are different type of heads available in the market, and again it depends upon the assembly, how you have to tight the bolt, what is the facility available, and these heads are generally based on those. So you buy it. If you look at the modern assemblies, like in bikes or all these things, they use generally the hexagonal internal heads, which use required L keys for that. So again it depends upon the company's own you can say design, whether you want to use the hexagonal heads, or whether you use the flat heads or philister heads, or whatever they want. This is the okay. Now if you look at the threaded, because if you look at the design of our threaded joints, so they contain actually threads, if you can see here, and these threads actually carries the major load, the stress in the bolted joints. So we need to understand the terminology, so then we have the idea what we are going to design. So threads have the topmost portions and the bottommost portion. Topmost portion is generally called as crusts, which means the outer surface, like this is the crust points, as I am meeting all these, and the roots are generally the lower points. So these are the roots. Clear? So the corner point is called root, the upper point is called the crust. The distance between two successive crust, between, let's say, distance between from this point to this point, this is called the pitch of the thread. And it could be small, it could be large, depending on the application. And the angle is, if you draw a parallel line from the slope here and here, the distance between is called the angle of the thread. And that is again very important, because the stressed area will always depend upon one of the most important factor in stress analysis is the angle of the thread. Then we have flank. Flank is generally the inclined part of the thread. It could be small, it could be large. And slope is the slope particular. So flank is the qualitative value, which means flank is this called the area at which slope is there, and slope is the value. What is the value of the slope? And for the whole bolt, if you measure from this root to this root, we call as minor diameter. So from this root to the other root, this is called the minor diameter of bolt. If you measure from crust to other crust, it's called the major diameter, and the average of these two is called the pitch diameter. So the distance between two roots is called the minor diameter. We generally call as core diameter, or we call as root diameters. It's the same thing for three. It's the same three different terminology for the same thing. So minor diameter also called as core diameter, also called as the root diameter. And we have a major diameter, generally called as nominal diameter. Major diameter is also termed as nominal diameter, and that is the distance from the between two crust on both sides. And the average of the major dia and minor dia is called as the pitch dia. Pitch dia generally is the dia which is used for the stress analysis. Okay, so as I mentioning earlier, that major dia also called as nominal diameter, where minor dia also called root diameter or core diameter. It's the same thing. If it's mentioned minor dia, it's the same thing. Core or root. And the pitch diameter is also called effective diameter because stress is actually applied on that pitch diameter. That's why it's also called as effective diameter. The pitch is generally defined as 1 over number of threads per unit length. So if you are, let's say, 5 threads per inch or 4 threads per inch, so divided that number by 1, you get it the pitch of the thread, the threaded joint. Okay, so there are certain standards that are used internationally for like V threads. V threads, by the way, are the most commonly used threads. If you look at screws, bolts, they're generally in car assemblies or industries. Generally, in assemblies we use V type threads. And V type threads have a different type, like this is called ANSI thread. This is American National Standard Institute thread. It has its own, this is by the way the angle of the thread, this is the pitch of the thread, this is the height of the crust, this is the height of the root, and all these things. This is the unified standard thread. So we have a height of, what is the height of the root, what is the height of the crust, and what is the angle. So it's the same thing. So these are different terminology. The standard threads we use for different industrial applications. Similarly, we have square thread, acme thread. Okay, square thread generally used, these are called as power threads. And if you require to transmit power, then these threads are used. So like lead screws in lathe machines or in other applications. So there could be a thread, and there could be a straight thread like the angle is 90 degree, or there could be a silent like the angle could be 29 degree, called acme threads. So there are other type of thread as well. Just to give an idea, and internationally we have different types of threads that are available, and these threads are again based on your application and your understanding that which thread to be used in which application. According to American National Standard Institute, we have the table which actually denotes gives you an idea that if you know the nominal diameter or major diameter of the thread of your threaded joint, which is 1.6234. By the way, these numbers are generally used in our market. So if you go to market, like if I want 10 bolt, this is very common. 10 ka bolt de de, 12 ka de de, 14 ka de de. So basically this 10, 12, 14 is the nominal diameter of the bolt, which means the outer diameter bolt is this number. So if you know the nominal diameter, then according to ANSI standards, you also know the pitch based on the standard value, and you also know the tensile area and the minor diameter. So these are the threads. If you have any nominal diameter available, you can actually find the diameters, the pitch, the tensile strength area, and the minor diameter. There are also two series, one called the coarse pitch series and called the fine pitch series. The coarse pitch series and the fine pitch series are generally used for different applications. Like in case of electrical assemblies, we use fine pitch series, which means that number of threads are larger per unit length. And for coarse pitch series, we use in cars assembly or like these. Both have its own significance. Okay. These are the ISO metric standard threads. Again, these standards are available. Now both have its own advantage and disadvantage. Like coarse or fine threads, coarse thread is generally very good in faster installations because it can be opened very quickly. It's more rugged. It can be used in rough environments, in humid environments. It's assembly very fast. Whereas fine threads, they are stronger than the coarse threads. Yes, they are used for fine adjustments, where coarse threads are not used for that. And one of the advantage of the fine thread, like you can see here, it's a coarse thread, it's a fine thread bolts. So one of the advantage is due to vibration, there is a very less loosening in the fine threads. But yes, the number of threads are larger, so we require large time for assembly and disassembly, which they are not very rugged. They cannot be used in very rough environments because the small size of the threads, because threads are large, number of threads are large, so the thread size is small, so it could quickly fail and result in the failure. So they are generally used in a very safe, in a low temperature, in a low humid environments, where generally temperatures or humidities or these are not very high. So again, everyone has its own application. If you know that you're using bolts in high humid applications like in boilers or all these things, then definitely yeah, high temperature use the coarse threads. Okay, so I will discuss this slide later, but if you look at the bolts, so bolts has the one of the stress that is beared by the bolt, which is actually uncommon with other types of joints, is the internal axial stress due to fastening. So what happens is that when you tight the bolt, so what you let's say you have a this is the head and you have a bolt here and you want to tighten a nut, so you just rotate the nut and nut try to move on this side, whereas you do not want your head to be moved, so you make it fixed, and when you tight it you want that your nut is moved so that your whatever is placed in between is tightened. Now what happens is when this is actually held in most of the cases held rigid, or you can held fixed the head of the bolt, this is the head of the bolt, and you want your nut to be rotated so that it tightened, so there is a force which actually try to stretch the bolt. Okay, you try to stretch the bolt or try to provide tension in the bolt, and that is actually the stress due to tightening, because these stresses are generally axial, so along the length. So these are called the internal stresses due to tightening. So when you tight the bolt, you want to stretch the bolt, because bolt tends to stretch because you are actually pulling shank through the nut. So the tightening, and for the bolt diameter less than, if your bolt diameter, this is the nominal diameter, if it is less than 18 mm, so the standard says that the tightening load, this piece called load, and I is called the internal axial stress load due to tightening. This load is written as 1420 times D, where D is the nominal diameter of bolt in millimeters, where D is the okay, just wait a minute. Oh yes, where D is the nominal diameter, we could generally call as dn to the nominal diameter, or just call as D, it's the same thing, and this must be in mm. This is what you have to remember. If you put this in a different unit, this will be wrong. So whenever you are trying to find the internal load due to tightening in the fluid tight joints where the D is less than 18 mm, you use Pi is equals to 1420 D, and the unit is in Newton. Whereas in case of fluid tight joints, if the D is greater than M18 or 18 mm, you use 284. Sorry, if I rub that. Okay, so if I rub that, so so if your D is greater than 18 M18, which is a metric standard, it's the same thing, M18 or 18 mm. The tightening load is slightly larger, which is the almost double of the small bolt, which is 2840. Again, D is the nominal diameter and must be actually put it in millimeters. So this is the idea, and the tension in the stress in the bolts is generally due to you can say, you know, that it is due to tension, and this tensile stress, which is because it's an axial force, a tensile force, it's a load which is this load divided by area. Now this area is the core area or the root area. So if you look at the bolt design, so we have threads like this on both sides. So the only area that bear the stress is from root to root, because that is a solid area that is available to bear the stress, or the minimum area that is available. So instead of using the outer diameter, we use the core or root diameter or minor diameter. So the stress is beared by the root diameter, which is the solid cylinder. Again, I am repeating this concept. So let's say if you have threads here on one side of the bolt, thread here on the other side of the bolts, See, if I draw a line here and draw a line here, so this area in between is a solid cylinder. So the stress that is beared is by this solid cylinder. This is why I'm highlighting. So the dia of this solid cylinder is dr or dc, whatever you call it, or dc. Clear? So the area is pi by 4. It's a perpendicular area because again this is the area we're talking about, this perpendicular area. But the diameter uses DC, which is the core diameter. And why it is used, again I am repeating, it is because this is the minimum solid diameter which actually bear the stress. Now total fastener load or total bolt load, in some book it called as PB, so don't confuse with that. It cannot PF. I prefer to use PF because I use the word fastener, which means the element which fastens it, which combines it, but you can use B as well, no problem. So PB, which is a total bolt load, this is the bolt load, is equals to initial tightening, which is this, again based on standards, plus K. Now K is a very interesting parameter. It's called the joint stiffness, or it's called joint constant. You can call it the joint constant. And P external is the any force that come due to pressure. Like if you told too tight joint, there will be some pressure that is going on. So total fastener load, which is here, which is this, is actually equals to the tightening load plus any external load, and that is joined through any joint material. Now this joint material could ranges from a very hard metals to very soft asbestos sheets. In case of, let's say, narrow copper ring, like just to give you an idea, this is the Suzuki-Mehran gasket. This is also the joint used to connect between cylinder block and the head of the engine. And if you look at the designs, this is a narrow copper ring around the cylinder lining. So what is the advantage? So if you look at the value, so the narrow copper ring provides a very lowest value of K, which is the advantage is if you put the value of K here, a low value, so the whole product become low, which means the actual load on fastener has been reduced. But if you see here, if I use a value like soft gaskets, so its value is nearly 1, which means that the joint does not provide any stress relieving to the bolts. So if you use hard metals like copper or all these things, like copper rings or lead gasket, you actually provides a very lower value of joint stiffness constant and or the joint constant, and then your total load is reduced because of this factor K, because K is directly multiplied with the external load. But if you're using a soft material like an asbestos or a simple hard, you can say जो गत्ता इस्तेमाल होता है हमारा, उसकी भी बनती है, जो सील्स बनती है या रबर की सील्स बनती है, the softer material generally do not carry as much stress as compared to the hard materials, and that's why K values for materials are generally higher, which means the load on the fastener is generally higher. This is, by the way, is the table. I have taken it from one lecture, but in your book this table is also mentioned, and it is a metal to metal joint with through bolts, so with this value of 0.0 to 0.1. Hard copper gaskets with long through bolts is 0.2 to 0.5. Soft copper gasket with long bolts for 0.5 to 0.75. Soft packing with bolts is 0.75 to 1, and soft packing with studs is nearly equal to 1. So again, when you solve the design problem, you have to see in which category this actually, and this could be where this A is called the ratio of the stiffness of the fastener divided by stiffness of the joint, and that is a very important term. So you have to keep remember that this A is nothing but KF over KJ. Clear? So KF is the stiffness constant of the fastener or the bolt, and KJ is the stiffness of your joint. Joint means if you have a cylinder head here, cylinder block here and the head here, in between you provide a gasket. This gasket, this with the solid red rectangle, This gasket is called the joint. It's a joint between the cylinder head and the cylinder block. So this joint has certain stiffness we call as Kj. So Kj is called the joint stiffness, Kf is called the fastener. So we use also fasteners to tighten it. So this is called the Kf is the fastener stiffness. So A is the ratio of the fastener stiffness over joint stiffness. So you always remember that formula. Okay, so we talked about this Mehran gasket. Okay, the bolts, as we discussed earlier, can fail under tension, and this is how the tension is applied on the bolts. If like in case of tightening, you provide an external force, so bolt tends to stretch, and the area is again taken as the lowest area, which is this area. I'm just highlighting here. This area, this diameter is called the core diameter from root to root. Clear? So we take the minimum area, which is the core area or the root area or the minimum area. So P over AC. And this is how this is just a picture. This is an actual picture of bolt failure using tension. So you can see a necking phenomena has gone on because these threads are generally straight, and as you have provided tension, so there is a necking. You can see a necking phenomena here, which means because they are manufactured from ductile materials. Yes, necking is very common, and you can also see necking phenomena here. And see, because of necking, there is a stretching in the bolts, and this is how then bolt ultimately failed due to tension. Okay, there could be also a possibility that the bolt itself will not fail, which means it will not break, but thread will be crushed. So if your thread is crushed, your bolt joint still fail. Why? Because if your nut become loose, because they do not actually you can say the threads are crushed from the bolt, your joint become loose, and when joint becomes loose, your failure is very prone to, like we have tightened, one of the common example is we use 4 bolts to tighten the car wheel with the hub. So if these 4 bolts, all the stress is beared by the threads. So if these threads are crushed, your tire will tends to actually remove from the hub during drive, and that is very dangerous. So the threads also will crush, and the idea of the crushing is that if you look at the bolts, so we have these bolts and we have threads here along the length. So see, there is a force which try to crush the threads perpendicular to the bolt area. So what is the area? Area is the pi by 4 d minor major minor d minor. So if you look at that area, if you look at what is this area equals to, so just magnify it so you can see easily. So this is how I magnified our diagram. So by the way, this is your D major, and this is your D minor. So if you subtract these two, you only get this area. This area contains only threads, and that's what's called pi by 4 d major square minus d minor square. And the crushing is because load is tension in direction, and the applied load is perpendicular to the thread area. It's not exactly perpendicular, but generally considered to be perpendicular. So they crush the threads, and the load is actually distributed among all threads equally. So if you have a nut of 7 threads, so stress is equally distributed among 7 threads. So to the total load, so instead of using the total load, we use the load per thread, and that is the why we use, if you have a fear that the bolt will fail because of the thread crushing, you can use bolt with a large number of threads, so that stress will be distributed among large number of threads. Okay, I think you have understood. It could also fail under shear, and how it can fail under shear. So see, if you have, again I'm just drawing so this is the idea of, so shearing is if load is like this, because load is actually applied in the tension. So if you translate the load on the threads, if this area is cut, it's tend to shear the thread. So area is this parallel to the force. So this is the area which we are talking about. This area is parallel to the force, and you want to find this area. So this is like a hoop. Yeah, this is like a hoop. Why like a hoop? Because see, this is the area which is trying to shear, and this is the area which tends to shear. So this is pi dh, and if you look at what is pi dh, pi dh, so it's area of a disk. It's a surface area of the disk. Surface area means pi d is this. So this whole area is pi circumference. Sorry, circumference is pi d. And what is our pi d minimum? Because we're talking about this from this root to this root. Pi d minimum is the circumference, and this is the area which is going to, because thread is all over the body of the bolt. So this area, surface area, tends to shear, and that's why you have to multiply with h, where h is the this, or we call as the pitch of the thread, height of the thread or the pitch of the, it's the same thing. So this a can be sheared. So area is now written as pi d, which is circumference of circle, times h, which is the pitch. So the shear can be, threads can also shear, but the area is very different from the area in crushing, because in area in crushing is the perpendicular area, where shear is the parallel area. So I hope from the last lecture of design of keys you have actually understood what I'm talking about. The areas are very critical in designing these boards, because these area actually gives you an idea that the how boards will fail, and which area they actually tends to fail. Okay, and this is how it occurs. If there could be also shear in bolt itself. So for example, if you have a load like this and the bolt is located, and so the bolt can also shear, cut down, is also shearing in the bolt. So we have a shearing in threads, and we also have possibility of the shearing of the bolt itself. So both are possible. Again, the area is different in both cases, because the orientation of area to the orientation of that area. Okay, so this is just a concept, not the part of the your you can say exam, but just to give an idea that the torsional shear stress caused by the frictional resistance of the thread during tightening. So when we tight the bolts, what we have to do, we actually shear it against the threads. So we have that particular resistance, which is because we are rotating it. So it's pi tau r equals to t over j. This is standard relation, and this by the way is called the shearing stress due to tightening, and that is 16 t over pi, where by the way this t is not the tightening torque, not the torque that rotational. This is a tightening torque. So, and this is the core diameter of the bolt. So this is an idea that there is a resistance during tightening, and the resistance is actually the shear stress generated by the resistance is 16 into t divided by pi d cube. And if you have a slightly bending in the bolt, because let's say if your plate is straight, let's say this is the first, second plate which is straight, and the first plate is slightly bended, although in the diagram it's more bended, but this is not the case. Bolts do not bend in a very large angles, but if you have a slight disorientation of both surfaces, there is a bending stress in the load, and that is actually estimated by xe over 2l, where x is the tilt of the bolt from its original neutral axis. This is E is the elasticity of the bolt, 2 is 2, and L is the length of the bolt. So this is the bending stress if bolts are not properly tightened, or if the surface are tightened, they are not parallel. So then you have additional bending stress, and that is dangerous for the bolt, because they can lead to failure. Okay, so if you have the combined tension and shear, let's say in bolt, so then you can have to design it based on these relations. And if you remember, you have done it with Mohr circle. So in Mohr circle, you have to find out these relations. Sigma max equals to sigma t by 2, which is the normal stress, 1 by 2 sigma t plus 4 tau square. Tau is the shear stress. Again, if you want to find maximum shear stress, so it's 1 by 2. You know that from Mohr circle, I know that. So this is the relations from Mohr circle. and based on these stresses you can find the, so whenever you're designing board you could this replace this sigma max by sigma naught. I'm just skipping those slides if you have to go through it, because these are the slides. They're not included in the exam because I've just given, if there's a dynamic loading like fluctuating loading, the design become more difficult, because then you have the maximum stress, alternating stress, and then you have a criteria like Soderberg diagram. Soderberg diagram actually have alternating component mean stress. There's a regions in which the region fail, and this is the criteria for the Soderberg criteria. So dynamic loading, as discussed in the class, is not the part of your course. It is generally taught in masters and PhD. Why? Because the dynamic loads have the criteria which are difficult to understand, and that's why it's generally not the part. So these two slides just give you an idea. If someone asks you what is the dynamic load and what is the criteria to design, so you know it's a Soderberg criteria. Soderberg is actually a very famous engineer who actually developed these relations to estimate the stresses in low bolts due to dynamic loading. Okay, so we are now coming to design of bolts. Now we have two types of design, and now we have to discuss that. One is called the fluid tight joints or the cylinder joints. These joints are generally the bolts are used in which you have a high pressure fluid. So you have a fluid with high pressure. So generally these pressure applied on the cover, and this cover you held this cover by means of number of bolts 2, 4, 6, 8, 16, 20. Clear? So we have these kind of bolts, and always in these joints we have the in between head. This is the cover plate of the head, and this is the main cylinder part. You always have a joint. So either use a soft gasket or a hard gasket or a seal or whatever you want, but there's always between the covers and the cylinders you have those kinds of joints. So your bolts in case of fluid tight joints. Other bolts we will study is the structural joints like brackets. So if you want to attach a bracket like the bracket mounted brackets like the outer unit of your AC or the overhead cranes, or these assembled by the bolts, these are generally called as structural joints. So their design is very much different from the design of the bolts that are used in fluid tight joints. So in this part of this lecture we will cover the fluid tight joint design, and then in the next lecture we'll cover the design based on the brackets or the generally called structural bolt joints. I think instead of going to this theory, I will just jump to a numerical, and in that numerical I will just highlight these relations that this is written in these problems. So let's come through this problem. So we have a time of only one problem, and if you know that from I have actually uploaded this lecture that the solution is already uploaded. One of the solution of this is uploaded in the classroom, and I just want you to please go through this the solution, and if you have any problem in understanding of these, please come to me. But this is very important regarding your exams. And there are other problems which you have to solve yourself. These are two problems, and then we have bracket joints. So I will just solve one problem, and that is this problem. Okay? So I will prefer to use the I will just prefer to use the okay, I prefer to use this sheet so I can solve it. So first I will import the numerical problem. So this is our numerical problem. This is written here, so you can see here. So so the problem says that you have so what you want to do is to analyze and design the bolts along with the cover plate. So we have, if you look at the assembly, so these are very large pressure vessels Pressure vessels are generally used to carry, used to enclose a very high pressure gases, and these are called inspection holes. These inspections are generally used to inspect the internal side where there is a corrosion or any abnormal activity or a fire, all these things inside a cylinder. And these is held by means of, you can see a lot of bolts here. You see, these are all bolts. So this is a cover plate over it. So you have a cover plate, and then you fasten the cover plate using a bolt joints. So you know that the stress that is applied on this cover plate and actually beared by the bolt. So the idea is analyze and design the bolts along with cover plate. So if you design the bolts and the cover plate for a pressure vessel, so this is your whole pressure vessel, a big pressure vessel with a wall thickness of 10 mm. So the pressure vessel which has a wall 10 mm thickness, you have to, this is known, and the effective diameter is 200 mm. So total diameter, this is the total diameter of the cylinder, which is the diameter in which gas is held, is 200 mm. Don't compare it with these large. This is just to give an example of the how these joints are used, but the effective diameter, which is diameter in which fluid can apply a load, is 200 mm, and the inside pressure of this of the gas is 15 bars. 15 bars is roughly 1.5 megapascal. 15 bars are very generally not a very high pressure, but you can say an average pressure, but certainly higher, because in your car tires the pressure is roughly about 3 bars. So 15 bars is a large number, and the joint is leak proof. So this is the idea you have to do. The joint must be leak proof, with the fastener stiffness being 1/5 of the joint stiffness. So instead of giving you the direct value of the joint constant, they have actually told you that the fastener stiffness is actually 1/5 of the joint stiffness. Generally, the Kf is always greater than less than Kj, because of the dimensions. The bolts are very large in length, and the joint is very small in thickness, so the stiffness of the joints are generally higher than these bolts. The cover plate is held by means of 8 studs. So 8 studs are used. Assume the same material for bolts and the cover plate. Studs are, yield strength of stud material is 400 megapascal. So there is no mentioning of the factor of safety in this problem. So you can use the factor of safety whatever you want. It is again up to you. The all formulas will be given, so don't remember those formulas. The idea is to just understand the relations. So let's start with the solution. So the first thing, you know that the if I just give me 1 minute. Okay. So first thing we have to do is find the allowable shear stress, which is sigma yield over factor of safety. So if sigma yield is 400, so 400 divided by, I take a factor of safety of 2. You can take up to I've told you that if human risk is involved, you can take up to 4, but human risk is not there, and there's dynamic load. Generally 1.25 to 2 is a very reasonable way. So you can 1.5, 1.8. I just take it as 2. So it's 200 megapascal. This is the allowable stress. Okay, now you have to design a bolt. So design of a bolt generally means that you have to find the core diameter or nominal diameter of bolt. This is what we talk about. We are not interested in the length of the bolt, because length can vary and the stress cannot be here by all the length. So if you have, let's say, give you an idea what I am talking about. Let's say this is the nut and this is the bolt. So we have thread in nut, thread in the bolts, and we tighten it. So the whole area, this area is not under stress. Clear? Because this is out of the nut. The only stress that is beared by this assembly is the threads that are connected within the nut. So the lengths are generally not the concern. generally not the concern. And yes, you can design the threads as well, but the design of threads is a difficult part. So instead of let's say going into the thread design, if we know the diameter of the bolt, we can go to the market and then we can take the standard threads like Beatrix standards or the British standards. We can take the standard thread and they works fine, no problem. So generally in design problems, I'm talking about generally, you have to design the core diameter or the nominal diameter. So please remember this. Please remember this. If someone asks you to design the bolts, we are interested in the diameters, not the lengths, because lengths is tricky. Length could be provided due to assembly, but stress length is very low in bolts. Okay, the formula we know is PF equals to PI plus K time P external. In my problem it is C, so please correct it to K. It's the same thing. I just write it K here. This is called joint constant. So PF is the total fastener load, PI is a tightening load, and K is P external is the load due to external load. Now this load, now this is a very interesting concept here. This is the load. This is the load on one fastener, one bolt. This is the load on the one bolt. Remember this, please remember this. If you will confuse that, your problem will become wrong. It will become a major fault. It has a major fault. So this is the load on the one bolt. This load is the tightening load of one bolt. This is the load carried by all the bolts. Why? If you look at this diagram, if I apply a pressure on this cover plate, so there could be 6 bolts, so this pressure is equally divided among all bolts. So that's why in this relation, the P external is the external load, which is load due to pressure, is equally distributed among all bolts. Clear? And that's why this formula can be modified as Pi plus K times P external over N. Why I divide by N? Now this has become load per, this has become load per bolt. Why I have divided by number of bolts? Because I know the external pressure, which is pressure due to fluid. He don't know about bolts. He apply the pressure, and a pressure then equally distributed among all bolts. At least in theory, we actually consider this practical. It's almost near practical as well. So instead of using relation of P external divide by N. Now I hope you understood this point, and this is critical. Now PF is the, if you look at the which kind of stress will be there. So if a pressure is applied on this head, this cover plate tends to pull out. The tendency of this cover plate is to pull out, and due to pulling you have a tension in the bolts. For sure, मतलब अगर आप इसको गौर से देखें तो आपको फील होगा कि there is a tension between bolts because cover plates are to push up because there is a high pressure inside this cylinder. So you can say it's pi by 4. Okay, so instead of writing it directly, you may got confused with this directly load. So just write here stress. So tensile stress is PF, which is fastener load divided by area, which is the core area. So the PF, which is the fastener load in one fastener, is sigma T times AC. So AC is pi by 4 DC square. Again, the area is perpendicular, and core diameter, because it's the lowest diameter we have to consider, times the tensile stress. And tensile stress can be written as tau allowable. This tau allowable is the allowable stress. That is the stress you have to use. because this is the stress, sorry, this is what we have written, this is the allowable stress they have to use. And I've told you in the design of keys that whenever you are designing the any machine element, you have to replace stresses by the allowable stresses. Okay, what is pi? Now you got confused that, sir, we don't know about diameter, so how we can select pi? Either it's 1420 d or pi is equals to 2480 d. Yes, we don't know the diameter, so you can use both, but it's preferable to use the higher value. Well, if you don't know and you see pressure is high, it's a general consideration that you use a higher value for the initial load. And the K, which is called a joint stiffness, is called as A over 1 plus A, where A, as I told you, is nothing but Kf over Kj, where Kf is the so if and in problem, if you look at the problem says that the joint stiffness, the fastest stiffness is 1/5 of the joint stiffness. So we can say that the joint stiffness, the fastener stiffness, is 1/5 of the joint stiffness. So which means that Kj is equals to 5 Kf from the information we have. So Kf equals to Kj equals to 5 Kf. If you find out this value, so Kf F over 5 Kf. Clear? So Kf over 5 Kf, this will become 1 over 5, and that is equals to 0.2. Clear? So A is 0.2. Let's put this value here, 0.2 over 1 plus 0.2, and just find out the value. 0.2 divided by 0.2 divided by 1.2, you get an answer of 0.167. So the K is 0.167. One of the another check for this value, this will always be less than 1. Sorry, less than 1. This value of K, always remember, will be less than 1. If this value is become greater than 1, you have doing this problem in a wrong way. You have done some fault, you have to revisit your problem. This cannot be, the value of K cannot be larger than 1. At most it can be equal to 1. At most. Which means all the load is carried by the bolts. The joint is doing nothing to reduce the load. Fine, it happens in most, like in very soft gaskets, like अगर आप गत्ता इस्तेमाल करते हैं, ये भी इस्तेमाल होता है कार्बोरेटर की सीलिंग में. कार्बोरेटर में फ्लूइड होता है, एयर होती है, मिक्सचर होता है, उसमें इस्तेमाल करने के लिए गत्ता इस्तेमाल करते हैं, जो आपका कॉपी गत्ता होता है. ये एस्बेस्टॉस मटेरियल बड़ा लाइट होता है, तो इसकी वैल्यू 0.98 कुछ होती है, लेकिन वो 1 के करीब ही होती है, तो वो कोई इतना लोड बर्दाश्त नहीं करती है, वो सिर्फ सील करती है. तो इट हैपन्स, बट अगेन दिस वैल्यू विल बी ऑलवेज लेस देन 1. तो ये आपने याद रखना है. अगर आपने कहीं इसको गलत कर दिया वो, तो फिर बता रहा कि कहीं गलत आ जाएगा. ओके, सो आई जस्ट राइट हेयर, मैं इसको लिख रहा हूँ दोबारा ताकि यू विल बी मोर क्लियर. नाउ अगेन रिलेशन, सो पी एफ इक्वल्स टू पी आई प्लस के टाइम पी एक्सटर्नल डिवाइड बाय एन. अगेन रिमेंबर दैट. सो पाई बाय 4 डी सी स्क्वायर इंटू टावर सिग्मा अलाउेबल equals to 2840d, where d is the nominal diameter, plus this value is 0.167. And okay, external pressure. Now external pressure, external load, sorry, not pressure. So we know pressure is equals to load over area, and then external load is nothing but pressure into area. Which area to be used, and that again in design that is the key understanding. So this is your cylinder and this is your cover plate. Sorry, this is your cover plate. So the only area that is exposed to this cover plate is this area, because fluid pressure can only be applied on this area which is exposed. So this area, which is this diameter, is only apply pressure on the cover plate. So the area exposed to the cylinder is pi by 4 capital D square. The capital D is the internal diameter of the cylinder. This is the cylinder. This is exposed area where gas can only apply pressure. So this is pi by 4. So pressure into pi by 4 and capital D square. Why capital D square? Again, this is the capital D is the internal diameter of this cylinder, and the only area exposed to the cover plate is this area. It divided by N. Now N in this case is R8. So now I'm putting the value. Now if you look at the whole problem, the designed value is DC. So this is we have to find. So but in one problem we have DC, in another problem we have D. So as per standards, DC is roughly 0.84 times D. This is as per standards. So either you can replace D by DC or DC by D. So it's up to you. Because if you replace D by DC, the answer will be the core diameter. If you replace DC by D, the answer will be in nominal diameter. So it's the same, it's no problem. So I just replace D by DC. So D is DC 0 by this value, which is, so just put the value here. So pi by 4 DC square sigma allowable equals to 2840 times 0.84. Sorry. So that is my mistake. Sorry. So D is equals to DC by 0.84. So here I can write 2840 and D is replaced by this DC divided by 0.84 plus 0.167 P into pi by 4 capital D square divided by 8. This is the equation. From that equation, now we put the values. Pi by 4 DC square is not known. Sigma allowable in standard units is 200. So 200 into 10 to the power 6 is equals to 2840. And if you remember, I have told you that just hold on. Okay, so one of the problem with this problem is, if you remember from the lecture we are going to solving this, that this must be in mm. If you remember, the standard says that the internal load must be in mm. So now this become a tricky part. Either you convert all of your, like if this is mm, this must be in mm, this must be Newton per millimeter square, this must be in Newton per millimeter square, this must be in millimeters. Or you convert D into meters and then everything will be in meters. So I think the best practice or the best thing is you convert all into millimeters. You can do otherwise, it's the same thing. So pi by 4 DC square, sigma allowable is 200, and as remember I've told you that megapascal is nothing but Newton per millimeter square. So I've taken instead of Newton per millimeter square. So 2840 divided by 0.84 times DC plus 0.167 into, now pressure is 15 bar. Now bar is not the standard unit. So if you convert the bar into standard units, so it's equals to 1.5 Newton per millimeter square. How do you know that? because 1 bar is equals to 10 raised to power 5 Newton per meter square. Clear? So 1.1 bar is 1 megapascal or Newton per millimeter square. So multiply 0.1 by 15 is 1.5. So 1.5 into pi by 4. This D is the capital diameter, which is the effective diameter of the cylinder. As you can see here, effective diameter of cylinder is 200. So just use in millimeters. 200 square divided by 8. I hope you have actually understood this. I hope. So if you find those values using calculator, so pi divided by 64, sorry, pi divided by 4 into 200, oh, this is square, sorry, not square. 200 is 157. So 157 DC square is equals to 2840 divided by 0.84 is 3380.9, which is 3380.9 DC, and this whole number you can calculate the number, which is 1.5 into pi into 200 square divided by 8 into 0.167 is 3 okay, let's calculate again. Just hold on. So 3.14 into 200 square into 1.5 divided by 8 divided by 4 into 0.167 is 983.2. So 983.2, this is your equation. If you look at the shape of this equation actually becomes a quadratic equation. Clear? So 157 DC square minus 3380.9 DC minus 983.2 equals to 0. This has become quadratic equation. Now I think since your school you have just want to find the application of quadratic formula, and I've actually heard from number of students from school or college, what is the advantage of quadratic formula, why are you using it. So see, quadratic formulas, the people who have developed these formulas have practical application, and as you can see here, without the quadratic formula you are unable to find the required bolt diameter, and that is the beauty of this equation. And that without using this quadratic formula you cannot be able to find the required bolt diameter, and that is one of the biggest application of quadratic formula or quadratic equation. If I divide this by 157 from the whole, so they become DC square minus 21.5 DC minus 6.26 equals to 0. If you solve this formula, you find DC equals to 21.8 or minus 0.3. Now minus 0.3 is not possible because we have to find diameter of bolt. This is 21.8 mm. This is the core diameter of the bolt. In other words, if you want to find nominal diameter, which by the way is the market standard, so nominal diameter is 0.84, so times this, so D is DC divided by 0.84, so this is 21.8 divided by 0.84, So you get an answer of 25.95 millimeter, and then you can say we have to use M16 bolt. 16 is M26 bolt. 26 is the closest whole number to this 25.95. So if you got, let's say, 25.1, you go to the next round number, which is 26. If your answer is 19.8, so 19.8 bolt is not available, but 20 bolt is available. So M26 bolt. Now M26 is a metric standard, and 26 means the nominal diameter of the bolt is 26 mm. So if you go to a shop, the hardware shop, and ask him that I want a 26 number bolt, he will give you that bolt. So but how do you come to this number? That is based on your understanding of how we have to design bolts. This problem come in a different sense as well. You may know the number of bolt, you may know the core diameter of bolt, but you don't know the number of bolts. I'm again repeating. You may know the diameter of bolt, which is, let's say I've used M16 bolts. M16 bolt means nominal diameter bolt is 16 mm. Now what I don't know is the number of bolt to be used. So then you have to find n from this formula. The formula remains the same. You have to do the same relation all the times, but now you have to find the n. Clear? And that is very simple than this. There could be a possibility that you don't know the number, you don't know the diameter as well, so both are unknown. So then you have to assume one thing. There is no other way out. So if it's a problem, you don't know the diameter of bolt, either the core diameter or the diameter, and you even don't know the number of the bolts, and the formula is the same. Then either you take any suitable value for diameter and then find the number of bolts, or the good thing is, or the practical thing is, you assume the number of bolts, which means standard use are 8, 12, 16, 20, 24. There are standard numbers to be used. So based on those numbers, you can find the the diameter of the bolt. So this is 2-3 possibilities that I want to discuss along with this problem. Okay, now the bolt has been designed. We know 8 bolts of 26 mm to be used. Now we have to design the cover plate. Now there are certain relations you have seen the slides, and I just encourage you to go those slides as well. But before that, if you allow me, I just take out one figure. Just give me 1 minute. Okay, let's see if the figure has been imported. No. Okay. Okay, I have to close it, then open it again. Sorry for that, for disturbance. And I have to load my okay. So this is what I want to import this picture, because then all the calculation is based on this picture. So okay, instead of now we have to find the standard dimensions. How we find the standard dimensions? Now we know what is the design of the bolt. Now look at this problem. Okay, so D1, which is the diameter of the hole, because generally uh, the the holes in which threadeds are not provided, we provide a slightly larger hole, and as per standards this hole must be at least 1 mm larger than the size of the 1 mm larger than the size. This is the standard. If you want to drill a hole for the bolt, always remember the standard says it must be 1 mm greater than your standard value. So which is 26 is the nominal diameter. Just add 1 mm, so you get a hole diameter of 27 mm. Now you know that the drill hole that you have to provide with the cover plate must be 27 mm. The second is called the pitch diameter, which is between two bolts on the either edge. So dp, which is the pitch diameter, is, if you just see that, it is equals to d, which is this. So this is d. Just draw lines, plus the thickness of these plates on the other side, which is 2 times t. So you see t here and t here, plus distance from this side to the center of the bolt, which is 1.5 d, plus 2 into 1.5 times d1. I hope you remember. I hope you understood that. The pitch diameter, which distance between one center of the bolt to the other center of bolt, can be found by effective diameter, which is the diameter of cylinder, plus the thickness of the wall of the cylinder, which is on either side is 2t, plus distance from the edge of the wall to the center of bolt is 1.5 d1 and 1.5 point d1 on the other side. Clear? So this is 200 is the d. Thickness is, we know from relation, is 10 millimeter, and d1 is, we have calculated earlier, is 1.5 times d1 is 27. So the distance between two consecutive bolts on the other side must be 301 mm. Now we know this as well. Now it moves towards the other calculations. Now another thing we have to find is a circumferential pitch. The circumferential pitch, let's say we have a cover plate, because cover is generally round, so we have, let's say, 6 bolts. This is the circumference. This is between two consecutive bolts in a circle. So this is a circle. This is called circumferential pitch, and that can be found out, because this is where the circle will be formed on the center, from the center of the bolts. So this is pi dp, which is the pitch circle of the bolt divided by n. So you can actually you can extract this formula. That is not a standard formula. This is the pitch circle. This diameter is the pitch diameter, which is same as this, divided by number of bolts. To pi dp is 301, n is 8. You get this between 118.1 millimeter. Standard says that if your design is leak proof, your CP must lie within the range of 20 under root d1 to 30 under root d1. As per standards, this is a check value. You want to check that so we find both ranges, see whether 118 mm. So 20 under root m1 is 20, under root d1 is 27. So this value is 103.9 millimeter, and this value is 155.8 millimeter. See, our values lie in between 118.1. So it's a leak proof. But if your design is not leak proof, at least in exams, you just write here how it can be leak proof. If you will see whether you have to increase d1 or not, whether you have to change other parameters or not, whether you have to decrease dp or not. You have to provide suggestions in one or two lines. You have do not ideally you have to calculate this again, but it's difficult to calculate. So the idea is to give you suggestion like you can say that if I increase d1, I could get a value depending upon the values that you can see here. If I use if I increase dp, I can just get a value close to this. If I increase the number of bolts, I can. So these are suggestions, you do not have to do it. The last thing that we have to do, the last thing we have to do is try to design the thickness of the cover plate. So cover plate dimensions are nodes. So first we have to find d naught. D naught is the, so if this is the cover plate, d naught is the outer diameter of the cover plate. And it's again very simple from the diagram. So diagram says that d naught is dp plus distance from this point to this point. So plus 2 times 1.5 d1. It's very simple. Why? Because see, this is written from this line to this line d1, again from this line to this d1. So just add 2 times. So outer diameter of your cover plate is 301 plus 3 into 27. Yes, that is equals to 382 millimeter. So your cover plate, the outer diameter cover plate must be 382 millimeters. Now the thing that is important in this problem is find the design of, you have to design the thickness of the cover plate. For that you have to just understand this relation. Okay, and this diagram is very important, so please focus on this diagram, not on this. Delete it for once. I just want to import the main diagram so that you can understand. So this is your main diagram. From the top view, this is the top view of the cylinder cover. So we have 2 different points. The X is called as, okay, so we have to cut this curve. So cover plate is actually circular. We have to cut into half. Why we have cut into half? Because it's symmetric. Either you can cut on this axis or this axis. In both these axes or in both these planes, you can say, okay, I have to draw it again, and just if you want to just use I think, let's look at this. Okay, going into detail, just so if you have a whole plate like this and you have number of bolts like 3, 4, 5, 6, and I can divide this here. Clear? So you have as per standards you have 2 load centers. So because symmetry I cut this plate, so we have one point which is y, second point is x, and this, by the way, this is the center of the bolt. So one center could be, bolt could be here, one could be here, and one could be here, and similar is the case on the other side. So this is a half plate. This is the O point, which this is section A through which we cut this. So this is A. So we cut this bolt plate into half. Now if you look at 3 bolts, it has a load center, because if 3 bolts are there, so they generally makes a triangle like this. There is a centroid of this triangle. As per standard, it says that this triangle must lies on X. Clear? This centroid of the bolt pattern, and that is, as per standard, is must be equal to 0.318 dp diametral pitch. Okay, diametral pitch, and that as per standard says, and this Y is the center for the pressure. So if I just draw this whole plate, you see same pressure is applied here, X is here, X bar, same Y is here, so the net will be the center. So net, because there are half plates, or net plate. So we have Y is the center of pressure for the gas, and X is the center of pressure for the bolt. So we have a distance. Now if you look at this, I want to draw here. So let's say in this is this line and this line, this is y, this is x. X is the centroid of the bolt pattern. I'm talking about the center line, half plate. So see what actually do this pressure tries to pull this plate out. So what pressure do actually is try to pull out, and whereas bolt try to keep it in. So bolts will try to keep the cover plate on position, whereas the pressure pull out. So there is a moment in between. So see, there is a bending. But the two different kinds of loads, there is a bending in the plate. I'm again repeating. The Y is the center pressure for the gas for the half plate, and X is the centroid of the bolt pattern on the half plate. So pressure will pull out the plate or try to apply force outward on the plate, whereas the bolt pattern try to keep this inward. That is the purpose of the bolts. If the both are applied outward, the pressure plate will burst. It will be ruptured. It will be fractured. The bolts try to keep the plate on the cylinder cover, which means that its direction is opposite. This provides a moment arm or the bending arm. So MAA, and the center is this. So the total this is the moment arm, which is half of the total bolt load divided by 2. And why half? Because half bolts are on this side, half bolts are on this side. So we have to, by total bolt load divided by, this is your force, and moment arm is simply this, which is OX minus OY. Why? Because OX is this distance, OY this distance, the rest is this distance, which is your moment arm. Now total bolt load. How we have to find the total bolt load? So if the just hold on. So the total bolt load, okay, just we have to find this value, total bolt load. So total bolt load is equals to, just I have to calculate once, then I will just communicate to you. Just give me some time for calculations. PI 2840 into 26 multiplied by 8 plus Okay, yes. The total bolt load is actually the total pressure applied on these bolts apart from the its tightening torque. Why? Because this moment is because of the pressure. Because pressure is applied, that's why moment is generated. So this total bolt load is the total P external on all bolts, which is pi by 4 d square into pressure. I hope you understood that point. The total bolt load is the pressure, is actually the pressure applied on all the bolts, and that is equals to pi by 4, d is 200 square, and pressure is 1.5 Newton per millimeter square. So just 200 square into 3.14 divided by 4 into 1.5. So it's 47,100 Newton. It's a total load due to pressure applied on the bolts. There are two loads. One load is applied due to you can say due to tightening, and second due to this. So here we have applied 47,100 divided to OX is 0.318 dp, 0.212 dp. This is oil and oxo. If you put this value, dp is known, you get an answer of 751,386.3 Newton millimeter or 751.38 Newton meter. This is the moment that is generated because of the pressure. Now based on that, okay, again we have to import the picture, which is this. All the time the picture is in front of you, otherwise you will not able to solve the problem, and this picture will be provided along with the numerical. Okay, what is the effective width of the plate, cover plate? Effective width. Now what is the effective width? So if I just draw a cover plate like this, so this is round like this. If from the side view it looks like this. It is thick but round in nature. So it has holes. So this is the width of the plate. But the effective width is, you have to subtract these diameters, hole diameters on the other side. मैं इसको इधर से I will cut it on, let's say किसी भी point से मैं cut करता हूँ इसको, इधर से या इधर से, ऐसे. तो this is equals to d naught minus 2d1. अभी minus 2d1 क्यों किया है? Why? Because you have to subtract these both holes because they contain no material. So effective width is d naught, which is 382 minus 2 times 27. So you have to subtract the holes you have to provide in the cover plate for the bolts. Effective width of the cover plate is 328 millimeter. 328 is 382 minus 54, 320. Yes. Now based on that, you have to find the thickness of the cover plate. Now because this provide bending, so you know bending stress is m over z, where z is the section modulus, and for the plate with the rectangular cross section or with the thickness of this, so the z is standard, which is for this kind of wave it is 1.6 times w effective times t, and thickness of cover plate is t1, so t1 square. Okay. By the way, for any rectangular cross section, the z value is 1.6 bd square, where b is this width and d is this depth. ठीक है? This is a standard if you look at table, and this will be given in the exam. So this is a standard value for any this thick cross section, rectangular cross section. So for this cross section, WB is written as W and D is written as T1 because there is a thickness here. So you know thickness is not known because you have to find the thickness, but width is known. So Z is equals to 54.7 T1 square in millimeter cube, because we just put the value in millimeters. Now we know that bending stress equals to M over Z. Now bending stress is again a normal stress, and normal stress can be written as sigma allowable. It's a normal stress. Again remember, bending stress is a normal stress. So M is, we know, which is 70. Now this is in mm cube, so I have to provide it in Newton millimeter. 751,386 751,386.3 divided by Z is 54.7 T1 square, and the sigma allowable is 200. Why? Because again you have to put it into millimeters, Newton per millimeter square, because the units on the right hand side. So if you solve this, T1 will come out to be 8.3 mm. This is quite reasonable. If the thickness of cylinder is 10 mm, so you can use a cover plate with 8.3 mm. If you confused with the units, you are wrong. Either it become a very large value or very small value. So you have to remember this. Clear? So this is the first part of our lecture. I will upload this lecture slides as well as the videos. I will provide it to you. So please go through this lecture, practice it. I will provide the notes as well, which I have written on the computer. Please go through this. If you have any problem, come to my class. I will not repeat this lecture again. You have to take this lecture, understand that lecture, practice the problem I have uploaded on the classroom, practice those problems that given the slides, so you have a more idea of how we design fluid tight joints. I hope you like this lecture. Thank you very much for your time, and we will meet inshallah in the class. Thank you very much.